Thank you for joining the meeting today. I'm very happy to see. I will start with the first presentation with an overview of our achievements within these 2 years of the project. The FORS project has as a main objective to develop new validated models able to issue forecasts and alerts for TIDs several hours ahead, exploiting observations from the solar corona, the interplanetary medium, the magnetosphere, the ionosphere, and the atmosphere. As you probably know, we had a previous project, the TechTide project, that was implemented from 2017 up to 2019. And in that project, we have developed methods to nowcast TIDs. And we have databases with the results of the nowcasting methods for TIDs, but also databases with the drivers of TIDs. So this was the basis for this new project, for the FORS project. The data sources that we are using are adjusted, of course, on the type of TIDs that we want to forecast. For large-scale TIDs, we use drivers from the solar wind, from the auroral oval, and from the middle to high latitude ionosphere. So we are using data from L1, from the image magnetometer array, and from the DLR tech gradient maps. We also use detected TID characteristics that we get from the HF interferometry method, a method that was developed in the frames of the TechTide project. And this method provides the spectral energy contribution of TIDs, and this is the SEC parameter, and our models that forecast large-scale TIDs target to this SEC parameter, to the forecasting of the SEC parameter. For the validation of our results, we use data from ionograms. Scaling characteristics from ionograms, but also in the inverted profile. And we also use DTEC keyograms. Now, for medium scale TIDs, we focus on the DTEC because in our understanding, the DTEC is a parameter that can that it is sensitive to disturbances from the bottom side, but also from above. And the deviation of the DTEC, it is used to detect the TID characteristics. And finally, the validation is done based on the ionogram traces, on continuous Doppler sounding data, and on feature from tech keyograms. The methodology in this project includes 3 action lines. The top line has to do with the method that it is applied to forecast, to develop forecasting methods for large-scale TIDs. And here we mainly rely on machine learning algorithms. After many experiments, we end up that the cut boosts and the temporal fusion transformers are the most suitable for the type of forecast that we want to do. The middle row refers to the method applied to issue forecasts for medium-scale TIDs. Here we calculate the climatology. This is the first step, the climatology of medium-scale TIDs. And then under some extreme cases basically triggered from the lower atmosphere, from volcano eruptions, or from earthquakes, we see some deviations from climatology, and these deviations with some criteria are considered to be some alerting situations for the users of applications concerns with medium-scale TIDs, and in this case, we issue alerts. In parallel, we are working to evaluate the suitability of these results with on-ground demonstration tests, and we will present also some results on that. Now, the large-scale TIDs are phenomena that we all know that start mainly from the auroral region and propagate towards the middle latitudes. So we are very lucky in our area in Europe because we have the image magnetometer data and using the IL and IU indices, we can have the first alert for the coming disturbance. The second alert is coming from the detrended GNSS tech at middle to high latitudes. And then the detection of the TIDs is done with the HF interferometry data. In this work, the classification of TID activity is based on the spectral energy contribution of the detected TIDs. So using as drivers what is detected at L1, then in the auroral oval, then at high latitudes, we end up to forecast the SEC that it is also detected at middle latitudes, and this detected SEC as used as features in our machine learning algorithms. We have two types of forecasting models. Both are classification models, so they are the results are binary. We can forecast the occurrence or not occurrence of large-scale TIDs, but of course we can set levels, thresholds of activity. So we can forecast what is expected with intensity more than 50%, or with intensity more than 70%, or with another threshold that it is user-defined. So we have one algorithm based on the cat boost, and this algorithm provides the forecast at the forecasted activity in Europe as one number that it is valid for the whole European region. So it is a general level of activity for the whole European region. The second method is based on temporal fusion transformers, and this method provides the SEC over Digison locations, so the user can choose among the locations where Digison operate and see and get the forecast. We have some demos about that later on. In general, the evaluation of the forecasted values are based on the recall and on the precision, but finally, the overall performance of the methods are calculated with the F1 score, which is the harmonic mean of the recall and of the precision. And in our experiments with using more classic classifiers and more advanced classifiers, we saw, for instance, that the TFT is one of the classifiers with the best performance among others. And also here, I would like to say that although we provide our forecast based on the F1 score, the user can choose among precision and recall in case the emphasis for the specific application is on the precision or on the accuracy. Regarding medium-scale TIDs, we have developed the climatological patterns of medium-scale TIDs for Europe, but again, over locations where we have DigiZone data. And why DigiZone data? Although we work with D20 tech, we wanted to have a way to validate the results. So this is why, provided that the validation is based on the ionogram features, we also provide the climatology over locations where we have DigiZone in operation. And here you can see the climatological pattern for the year 2023 for Prouchonice station, which is in the central of Europe. And you can see the climatological effect of the solar terminator. On the right side, you see how the D20 tech behaves when we have dynamic atmospheric phenomenon, and here is the case of a cold front passage occurred at the end of August 2023 in Central Europe. And these are the results for Prouchonice location. You can see with the black and red lines the climatological behavior in quartiles, first, second, and third. And with the green line and the blue line here, you can see the D-Tech, how much exceeds the climatology. And in such cases, we issue alerts. In parallel, as I said, we are working to evaluate the efficiency of our predictions, and to do so, we are conducting experiments. We had in some special campaigns, for example, between Nostradamus over the horizon radar and direction finding system in Germany. And in one of these special campaigns, there was a deviation in the azimuth of 26 degrees and even more. And this was a very important deviation. And we have seen that during the experiment, we had a substorm activity that led to the generation of TIDs. And these TIDs were successfully forecasted by the FORS method. This is the red line that you see here at the bottom. And the results are for Durb station, which is in the site of line between the over the horizon radar and the direction finding system. And the algorithm here, the forecast algorithm is set for the threshold of 70%. So this means that detect all the disturbances that are above 70%, and you see that the performance is very, very good. All these developments at some point have to be transitioned to operations. We have built a forecasting system in NOAA, which is still under development. I mean, it is a demo for forecasting system, but still we need to have storage for the data. We need to have a lot of processing power for the machine learning algorithms and for the empirical models. And the results are the MSTID forecast and the large-scale D forecast, but still the results are raw data, are not transitioned yet to operations. So to do so, we need to consider some standards that are recommended by the WMO, standards that are recommended by our PITHIA NRF e-science centers setup, which is basically the ontology, because we aim to register all the models from the T-Force at some point to be registered in PITHIA and to be processed through, to be accessed from PTI Science Center. We also need to consider real the actual requirements as designers and developers of the models. So we need to see how the data are streaming into our end, what is the latency, what are the storage requirements, how the interfaces with the data can be developed, how to clean the data, which is a huge issue. It's a project by its own, the data cleaning. How to provide to enhance the forecasting horizon, but maintaining some accuracy in the data, and what is the execution time for our models. And finally, for the end user of high-level data products, we have to consider requirements regarding the design of the high-level data products, the forecasting horizon, the accuracy, the availability of the result in real time, near real time, how much near is real time is the near real time for each application, and the requirement also for the user to access archive data and to have also quality indicators for our results. Now, speaking about the previous TechTide developments and the design of high-level data products, what we are thinking as an end format, as an end layout of our products, is something similar to what we have done for the TechTide products. For instance, in TechTide, we provide a map that gives to the user the direction of propagation of large-scale DIDs, and this is the result of the HF interferometry that it is developed by the Ebro Observatory, and it is implemented in real time in the ESA Space Weather Portal. So something similar to that can be done with the results of the machine learning models. And on top, of course, we can issue a general flag for the current and expected activity level over the whole European region. We can also provide the forecast over specific location. And here is again from the TechTide portal that shows that there is a drop-down menu and the user can select among the station and can get one graph for the whole day, which is updated with dynamically updated, and at the end of the day it is completed with all the measurements. But these plots are also available in the archive. And finally, to summarize this presentation, this first presentation, this is some information to be considered until and to be read and to be discussed again at the end of the day today in the discussion. So what we need to get as an information from this Innovation Day today are specific considerations from potential future end users. And I wrote down here some key points for this consideration. First is the design and format of the high-level data products. Second is the latency in respect to real time. Then we have the access to archive data. Do we need that or not? The preferred transfer protocol of our data to the end user. The forecasting horizon versus uncertainty. The requirement to specify the scale of TID. So what I mean is really important for the end user to know that the TID is large scale or medium scale, or the user wants to know only if we have a TID activity independent from the source of the TID. Then another point of concern is the access to the source code, the access to the input data that we use to run to retrain every time the machine learning data. And finally, any other considerations to allow deeper analysis and evaluation of the forecasts.